Hi everybody, I'm Rashid and I'll continue talking about this calculation of probabilities, and now we're getting to, let's talk about a point before we move on. I think we know this one, but we make sure that I emphasize it. But I'll just talk about the complement rule, and I did talk about the complement rule, the complement sets. So and I did it in the other example in the previous ones, the 7%, and so the operation is 93%. So if you want to see that video, so once you know a probability for an event, its complement is going to be 1 minus that, right? It's almost like and you can find the example in your textbook about birthdays if you want to check it. So for example, if something is 20%, what's remaining is 80%. So for 6.4, conditional probabilities is a topic that's kind of long, but it has very interesting applications. And here conditional means something, you'll see in this video, depends on something else. And the probability of an event depends often in a critical way on the sample space, of course, in question. So here we're going to explore this dependence in some detail by talking about this conditional probability. And I'll start with this example of college students. All right, and I put the Venn diagram for it because we have been using this union intersection for sets. So suppose that a certain mathematics class contains 26 students. Of these, 14 are economics major, 15 are first year students, and 7 are neither. So suppose that a person is selected at random from the class, all right? So so you can maybe do a chart if you want. So 26 is all kind, right? So in this sample space, 10 and 5 are 15, 15 and 4, that's 19, 19 plus 7 are 26, right? So if you do that, uh, 14 are economics, which means the E here, 10 and a 4. So you see, if you want to draw the Venn diagram, so it makes it easier for you to see. And 7, let's see, 15 are first year students. So economics, first year students, and 7 are neither. Suppose that a person is selected at random. So the first question, what is the probability that the person is both an economics major and first year student? What do you think? Right? You're looking at the intersection of the two, the economics and this. So you're looking at that intersection. So when we use this and, we're going straight for the intersection. So the probability of this, selecting a student, we have a sample space with 26 and the choice is random. All students are likely to be selected, of course. You see there is nothing about something else, some deviation from this. The event of economics major and first, so usually this is the probability we do this event of selecting student from and being so if I define it this way, right, then this probability of E let's just say the probability of let's make it clear. It's gonna be the number there over the sample space, which is 10 out of 26, which is 513. All right. So the probability of selecting is, you can divide it and of course and get this. Suppose that we are given the additional information that the person selected is a first year. All right. What is the probability that they are also economic major? So as you see in this question, you're given the information. Now you're given the information that the person that was selected is a first year. What is the probability that that they are also an economic majors? So if we know that, then the possible outcome of the experiment are restricted. They must belong to F, of course. And given, so now there is given that information, we must alter the sample space, right, to the first year students. So since each of the 15 first year students is equally likely to be selected, and since 10 out of the 15 first year students are economic majors, then the probability of choosing an economic major under these conditions is equal to 10 out of 15, right? So if you're given an information and it's restricted, it's not anymore that kind of guess thing where you apply the formula. You're given an information, you're using information, now you're kind of like the pinpoint is more targeted, is more. That's why you're gonna have a 10 out of 15, right? Because the question, if you go back to the question, suppose that we are given that the person selected is the first year student, right? Is the first year student. So we're talking out of the 15 now. It's almost like the new sample space is the 15. What is the probability that they are also an economics major? Well, in this 15, there are 10 of them only are 10 economic majors. You see how the story changed with the given information? So there is in math, and economics also, there is a theory that can be used to put a value on a given information and estimate the cost for that value or that addition value, that addition information that you need, and whether it's worth to spend money in getting the addition information or not. You want, for example, drilling or going into a market and you know your costs, whether this event happens and whether this event doesn't happen. But if you're given just another more information, you can have a better strategy. So you're gonna go ahead and invest in the information, and that's gonna cost money. And there is an economics formula to use for that. So I hope this problem here that worked on helps you better understand this story, right? So the gist of this is this conditional probability. All right, and I'll explain it. So let us consider this example 1. In part A, the sample space is the set of students in this math class. A is the event students is an economic measure, and F is in the event of student is first year, right? On the other hand, part B poses this question, student in first year student, the condition is satisfied, of course. So we are being asked to find the conditional probability of E given F, all right? So what we did in this example is find the probability of E given F, all right? Okay. So this is what we're gonna introduce in this conditional probability. And we restrict our attention to the new sample space that I draw here, right? This, all right. That didn't go well, but it's okay. We get the idea. So we consider only first year students and ask of these, what is the probability of choosing an economics major? So we assign this probability of E given F via the following formula. You see the probability of E intersection with F over the probability of F. So you see here, right? Provided, of course, that the probability of F is not 0. So it's not an impossible outcome there. So we will provide, of course, more details about this. And here is an example. So as usual, I'll work it out, try it out, talk it out, you know, and talk about it and go back and forth until it's clear. Of course, the patience is the important part here, because if we really want to understand this and be able to use it in the future, we have to invest time. Time is the important thing here, because time will link with the effort. The more time we spend, the more effort we put in, and once you have these two, then the better outcome we're going to have, which means the probability of success of understanding will increase. So 20% of employees of the Acme Steel Company are college grads, and of all of its employees, 25% earn more than 50% per year, and 50,000 and 15% are college grads earning more than 50,000. What is the probability that an employee selected at random earns more than 50,000 per year, given that they are a college grad? So you see, given that. So it's not that direct probability that we're talking about. So let's break it down by writing the events. Let's call this H. Those that earn more than 50,000 per year, right? And C is college grad. So what we are really asked is the probability that an employee selected at random earns more than 50,000, right? Given that they are a college grad, given that. So there is that condition, right? So let's bring down the formula. So the probability of H given C and are we, so let's look at this 25%. So 25% earn more than 50,000, which means here the probability of H is 0.25, right? And 15%, where is the other? Let's see. Let's take out this so we can see all the numbers here. And this other one is the intersection. 15% are college grads earning more than 50%, so the two. So the probability of the two, the intersection is 0.15. All right. So what is the probability of a college grad? It's not there, right? 20%, right? So this is the tricky part with the stories. Some are written, some are put as far as numbers. So you just gotta read it again. That's why I do this method with you, so so you can rescan until you collect all the given data for you to respond to the request. All right, so the PR of C here is 0.20 or 0.2. All right, so we can follow the formula and say the probability of H given C and the probability of C is 0.15 or 0.20. It's 3/4. So 3/4 of college grads at the steel company earn more than 50%, $50,000 per year. So and of course, one thing that I want to talk about is this product rule. If the probability of F, of course, not equal to 0, that the probability of this intersection E with F is equal to the probability of F times this. So where this come from? Well, it's not another new formula. It's just this, if you put this over 1, all right, and you cross multiply, you're gonna get this, this formula, right? So this is the same formula, it's just given in a form of the product rule, right? And we have more examples we can work on. We can do these other examples. So colorblind males assume that a certain school contains an equal number of female and male students, and that 5% of the male population is colorblind. So this is a good problem. So we are aware of this, right? And we know. So for example, if you're teaching or you're doing a presentation at work, if you keep this in mind, you're not going to pick these colors that maybe that may fall in this category, and somebody be in the audience and see the colors same, and you be pointing that, look, as you see in chart, for example, the red is this, and you know, so this is good to know and keep in mind this in presentations. So assume that a certain school contains an equal number of female and male students, and that 5% of the male population is colorblind. Find the probability that a randomly selected student, the probability, right? And it's not working. Let's switch, it didn't switch. The probability that a randomly selected student is a colorblind male, right? So there is a conditional, a condition. It's a conditional probability here. So we can use the same initials, male, right? We can use B for colorblind. And we're looking for, so we need to find the probability. Let's need to find first the probability of colorblind and intersection male, right? So this 0.05% is the male one. And so now let's see. Assume that a certain school contains an equal number of female and male, and that 5% of the male population is colorblind, right? This one here is this one here. Right. Find the probability that randomly selected student is a color blind male, right? So what is this 5%? So think about it for a second. This 5% is the male population is colorblind, right? So that's the probability of the 0.05 is that, right? And this will allow us to use this product rule, of course, because now this is what we need to find that is missing. And in this case, one number I didn't use yet. Yeah, so I'm looking at it, I'm like, which one is not correct here? Yeah, this one is not correct. So this is 50-50, right? 50 male, 50 female. So that's 50%, right? That's 50-50 mean, right? So the probability of individual to be male is 0.5, right? So that's the missing number there, all right? And this is 0.05, so what's left is just to apply this, and now I can go ahead and just multiply the two numbers and get 0.5 times 0.05, which is 0.025, all right? All right, so as you see, we're more interested in the upper formula than this one, but just the idea that if you have the other formula, it takes also this form, right? So this is in general, this is a rule in general if you're working with higher applications, all right? And you can see it in the textbook. So for this definition, let E and F be events. We say that E and F are independent, provided that the probability of E intersection F equal probability of E multiply with probability of F, all right? And of course, the probability of E and F should not be 0. And we can use this formula as well. And there are some other examples, but I think for the not to get this too long, I can talk about this other example here. So let's let E and F be events with non-zero probability. E and F are independent, provided that, of course, probability of E given F equals probability of E, and the other one equals probability of F. And let's see through this example here whether we need to find out whether they are independent. So for each pair of the probabilities, determine whether E and F are independent. An experiment consists of observing the outcome of 2 consecutive rolls of a die. Let E and F be the events. So E, the first roll is 3. F, the second roll is 6. All right. So if we clearly think about this, and as you see from the previous ones that I talked about, that the probability of E, of course, is same as the probability of F, which is 1/6, right? Because you have 6 faces there, and a 3 is 1 face, of course, right? And 6 is 1. So, and you have 6 total, so 1/6. So to compute this conditional probability, we're going to assume that F occurs, then there are 6 possible outcomes. All right. So the second roll is 6. So we're going to assume that it happens. So what are the outcomes that can happen? So let's look at it. So what's possible? 1 with 6, 2 with 6, right? We said 6 happened, right? 3 with 6, 4 with 6, 5 with 6, 6 with 6, right? So all the outcomes are likely. So what is the intersection here? If you see that the intersection is 3, 6, because the first roll is 3, the second is 6, so this is just 1. So E intersection with F is this 3, 6. And of course, once we know this, we can apply the formula, the probability of E. The first roll is 3, given that the second roll is 6. It's going to be this number over the other number of F, and which is same as the probability of E, right? And of course, if you do the same one, you'll find the same thing if you're looking for, which is the probability of F as well. So E and F are independent events in agreement with what we think, of course, right? So they are independent. So if you do the same thing here, it's going to be same as the probability of F. So they are independent. Okay. For question B, an experiment consists of observing results of drawing 2 consecutive cards from 52 card deck. Let E and F be the events. E is the second card is black. F is the first card is red. All right. So here they are the same numbers of outcomes with the second card red and with the second card black. So the probability of E is going to be half, right? And if we need to calculate this probability, this conditional probability, of course, we're going to need to note that if F occurs, then there are 51 equally likely choices for the second card, right? So because the deck has 52, and if one occurs, right? So if one occurs, then the remaining is 51 cards, right? So of which these 51 cards, 26 of course are black. So that the probability is going to be that 26 out of 51. So the probability that there, just as an example, just like the previous example we talked about, is going to be 26 out of 51 when now the restricted space. So as you see, these are not the same, right? This thing is not same as the probability of E, which is the 1/2. It's not the same. So are not independent. So not independent. All right, I think we go back, say that based on definition, the events E and F are independent, provided that you do the conditional probability equals to probability of E, and if you do the other way, you get equals to probability of F. In example E, that happened, and in example B, that didn't happen. All right, thank you.